Okay, welcome everybody to the second quantum cryptography session. Our first talk will be on cloning games, a general framework for unclonable primitives by Prabhanjan Ananth, Fatih Kalioglu, and Qipeng Liu. And Fatih will give the talk. Please take it away.
Yeah, thank you for the introduction. Hi, everyone. I'll talk about cloning games today. So I'll start with the no-cloning theorem. In quantum mechanics, it is impossible to clone arbitrary quantum states, whereas in the classical world, you can clone data as much as you want. And we also have some states satisfying no partial cloning, meaning given the quantum state, it's impossible to create two states, both of which can be used for the same functionality as the original state. And this is stronger than just the statement of the no cloning. Now, unclonable cryptography leverages states as such, and it's useful because it gives us unconditional separation of quantum from classical. And it does this by introducing novel technologies, such as quantum money, which is the quantum equivalent of physical money banknotes. And this is in contrast with trying to achieve quantum advantage through algorithms, in which case you end up having to make assumptions about the computational power of the classical side. Now, depending on the functionality we consider in the partial cloning, we get different unclonable primitives. For example, if you take an encryption scheme, and being a valid ciphertext or being a valid decryption key is the functionality you consider unclonable, we get primitives such as unclonable encryption and unclonable decryption keys. Similarly, if evaluating a hidden function on a given input is your unclonable functionality, it gives us quantum copy protection. And the list goes on with public key quantum money and so on. I'd like to note unclonable encryption, achieving it in the plain model without any assumptions has been a major open problem since it's been introduced. And achieving public key quantum money without heavy computational assumptions has been an even older and bigger open problem, which not only cryptographers, but many mathematicians attempted to solve. In this work, we'll focus on the first three primitives highlighted in green. So if you look at the prior work in unclonable cryptography, we'll notice that there are many complicated proofs, and non-experts might have a hard time understanding the details of those proofs. Also, there are many techniques that get to be reapplied in future work, but are applicable in only certain scenarios. Also, most of the works focus on the feasibility of several primitives, and there are much fewer works understanding which primitives imply which primitives. All in all, we can say that we need a more systematic study of this field. Now, on my third point, I'll elaborate more as to why we need more implication results. First of all, we want to understand what minimal assumptions are necessary in achieving each of these primitives. In the classical world, we've done a great job over the years having what we call Impagliazzo's 5 worlds. And this describes what scenarios are possible and what hierarchies of primitives we have. It's supported by numerous black box separation results, which we're still lacking in unclonable crypto. A second reason to care about the implications is understanding what types of states we can use as our unclonable states. And this is important because some states, like the Wisner states, are unentangled, more feasible in the near term, whereas coset states are highly entangled and potentially going to take much longer to achieve in the real world. And finally, in the classical world, we have standard techniques such as the hybrid method and the Goldreich-Levin extraction, which are commonly used to understand, for example, 1-bit to multi-bit implications of several primitives. And if you try to adapt these to the unclonability setting, you face several problems. It's good to understand whether these techniques are useful at all or under what conditions these are useful. So this brings us to our main conceptual contribution, which is a general framework to understand unclonable primitives called cloning games. And within this framework, we list several generic theorems. And as the corollaries of those theorems, we list our concrete results, which I'll talk about right now. The first result is we achieve the first one-time unconditionally secure construction of unclonable decryption keys in the plane model, whereas the prior work on this achieved it in a stronger public key setting, but using heavy computational assumptions such as post-quantum indistinguishability obfuscation. Our next result is achieving unclonable encryption and copy protection for single-bit point functions with respect to a random oracle using unentangled BB84 states, whereas prior work did the same thing using entangled coset states. And people have also considered different security notions and negative results for this primitive. And the next result, I'll talk more about it later in the talk, but it relates different security definitions for the same unclonable primitive. And it hasn't been done before. Finally, we have a new construction of encryption with certified deletion. And even though we knew how to do this without assumptions before, our work gives a new flavored construction and an arguably simpler security proof using more standard techniques like monogamy of entanglement. Right, so what do cloning games look like? Conceptually, it captures any scenario in which we have a quantum token, meaning a quantum state, that has two properties. One is that it's verifiable. Two, it's unclonable. And it's a security game, essentially, between a referee and a cloning adversary, which consists of three parties, Alice, Bob, and Charlie. It has three phases. In the first phase, called the setup phase, the referee will generate a quantum token and send it over to Alice. In the splitting phase, the Alice will apply a quantum channel to the quantum token and generate a bipartite state that is shared between Bob on the left and Charlie on the right. And this bipartite state is allowed to be entangled. However, the two parties are not allowed to communicate in the next phase, which is called the verification phase, in which the referee will interact with both Bob and Charlie by sending them each a challenge and receiving an answer. After that, the referee will verify each of their answers and accept or reject. Now, we require two properties from a cloning game: correctness and security. Correctness is essentially the verifiability. It says that there is some Alice, which given the quantum token, can pass the verification with probability close to 1. And security says in the verification phase, no matter what the adversary does, the probability that both answers get accepted is not much greater than what is trivially achievable. What do I mean by that? I mean what's possible by a trivial cloning attack, in which Alice doesn't attempt to clone this state, simply sends it over to Bob, and Charlie makes his best educated guess about the answer. Now, if the trivial success is close to 0, that's a cloning search game, and if it's close to 1/2, that's a cloning decision game, matching terminology in the classical world. And I said the goal is to capture unclonable primitives generally. Just to give a couple examples, unclonable encryption can be thought of as the token being a ciphertext, and the verification phase sending the secret key and expecting the message or some information about it in return. And in quantum copy protection, you copy protect the classical function f, and in the verification phase, you're supposed to take an input to this function and produce the evaluation of f on this input. And Similarly, you can capture almost all unclonable primitives. Now, if you recall, in the verification phase, both parties get a challenge. They need not be the same, and depending on how they're correlated, we have the independent challenge setting and the identical challenge setting. And with this, I'll describe our third result, which I skipped before, which says that for a general class of cloning games, if it's secure against independent challenges, it's also secure against identical challenges. And this class includes, for example, copy protection and unclonable decryption keys for certain parameter regimes. And for the rest of the talk, I'd like to talk about our techniques. So conceptually, our goal is to understand non-local reductions. And in particular, we want to understand reductions of the form where the inner adversary is a decision solver and the outer adversary is a search solver. And you'll recognize this from the famous Goldrake-Levin extraction. In the non-local setting, it would be trying to do this simultaneously for Bob and Charlie. Now, there are two main approaches we take in this paper, and they both build on previous work from Last Crypto. The first approach is considering the case when the reduction makes one query. And what's the main challenge in this setting? The challenge is if you try to perform a reduction on Bob, it might affect Charlie's outcome because of entanglement. So in previous work, should be 22, what they do is they first project this possibly entangled state onto what's called good states, meaning they have good eigenvalues for both parties. Now, if you can successfully do this, then even if you do something on Bob's register, Charlie will still remain in the good state regime. And how do you make sure this projection succeeds? It involves some techniques I won't go into details of, but essentially what you do is you reduce it to a strong version of unclonable search security, which we call augmented security. And prior work used this fact for coset states, which was already known. And in this work, we show that you can start with any weak unclonable search security and upgrade it to augmented security. In particular, we can instantiate it with BB84 states and achieve copy protection and unclonable encryption in the random oracle model using unentangled BB84 states. Now, just a bit more in detail, we consider search games where both Bob and Charlie are asked to output a high min entropy message M. And augmented security means we give the adversary more power by letting all parties quantum query an oracle, which tells you whether your query equals the hidden message M or not. So in summary, what we do can be thought of taking the prior work and replacing the first step with coset states and instantiating it more generally from any weakly unclonable states. And because we know Wiesner or BB84 states are a valid candidate for that due to Broadbent and Lord, we achieved the results from unentangled states. Now on to the second approach. It's the case when the reduction for one party makes multiple queries to the inner adversary. Now, if you attended the previous session, you might remember that if you query a quantum algorithm, its internal state might be disturbed. And this means if you make additional queries, the success probability might be lower than before. So prior work by Vitansky et al. Overcomes this issue by lifting classical black box non-adaptive reductions to the quantum setting. And in this work, we generalize their lifting theorem to the non-local setting. Now, the key step in their proof is to take a quantum solver and make it persistent, meaning it can solve multiple instances of the same problem. And the main challenge is to do this even in the non-local setting, even if Bob and Charlie share entangled states. In more detail, what they do is they run the state once, they run the solver once, and they repair the state, recovering not necessarily the original state, but a state that has close success probability to the original state. And our approach is very natural. It's simply do this for both Bob and Charlie and hope for the best. Now, the main technical idea is to show that this works even if the states are entangled. And here's a high-level summary of why it works. It's by observing that if you consider the Jordan decompositions of Bob's and Charlie's registers, the projection onto the Jordan subspaces commute with the state repair procedure. So you can assume it's performed without performing any repairs, without loss of generality. Now, also we observe that that projection unentangles the state. And once the state is unentangled, you can do a convexity argument to show that locally repairing each register actually globally repairs the state. So in summary, what we do in non-local lifting is we locally repair each of Bob and Charlie. And as long as we're in the independent challenge setting, we can show that it still works by looking at the Jordan decompositions. As corollaries of the non-local lifting theorem, we get our first and the third results. And just to recap, that is one-time unclonable decryption keys construction. And also the theorem that says a class of cloning games, independent challenge secure, are also identical challenge secure. And the construction of unclonable decryption keys looks like this. And the main idea is that it combines weak unclonable security with simultaneous quantum Goldrake-Levin, which follows as a corollary of the non-local lifting. So we start with classical Goldrake-Levin, lift it to simultaneous quantum Goldrake-Levin, and combine it with a weakly unclonable secure construction to achieve this. And I will conclude by stating some open problems. The first one is our theorem stating the relationship between independent and identical challenges. It has this restriction of being evasive. For example, if you consider copy protection, you need to require that the outputs are long strings. And whether we can remove this is an open problem. Also, in our results, with regards to constructions in the quantum random oracle model, instantiating these oracles would solve long-standing open problems, and that's in another direction. And finally, from the prior work, we inherit these restrictions of black box and non-adaptive when we lift reductions. So can we actually get rid of those restrictions is another open problem. And that's the end of the talk. Thank you for listening.
Great, thank you for the talk. We've got time for some questions.
Hi, thanks for the talk. I think you mentioned that you could capture almost all unclonable primitives using your cloning games. So what primitives are left and why can't you capture those?
So as far as we can tell, we can capture everything by suitably making small modifications, but we don't want to make too bold of a claim. That's why we say almost, yeah.
Okay, then can you imagine creating any other types of primitives that don't fit into your framework? Do you think that's interesting to try?
Sure. You mean in unclonable crypto or? Yeah, as I said, as far as we can tell, in unclonable crypto, it should capture everything by maybe some syntactical changes. But for example, in quantum crypto, stuff like quantum key distribution don't necessarily fit into this framework. Yeah.
Thanks very much.
Thank you.
Okay, great. Let's thank our speaker again. Okay, great. Oh, looks like we've lost our AV here. Great. Our last talk of this session is Publicly Verifiable Deletion via Target Collapsing Functions by James Bartosek, Dakshita Khurana, and Alexander Paremba. And Alex will give the talk.
Yeah, thank you so much. Okay, I want to start with a question. Can we prove that data has been deleted? So in the classical world of bits, which are either 0 or 1, there's not much we can do. But it turns out that in the quantum model of computation, proving deletion is actually possible, provided that the data is encrypted using a quantum state. So this brings us to this really cool idea that was proposed by Broadbent and Islam. So it's called quantum encryption with certified deletion, and we have two parties. And suppose that Alice has some data that she wants to encrypt. Let's say it's some contract. And she wants Bob to hold on to an encryption of this contract. And this ciphertext will be a quantum state because we don't want Bob to copy it. Okay? And what certified deletion allows Alice to do is to ask Bob to delete the ciphertext, in which case Bob will measure it and produce some certificate pi that Alice can verify. And if Alice is convinced that pi is a valid certificate, then the security guarantee says that essentially Bob has no information left about which message was encrypted. So Alice could, in principle, just leak the secret key, and Bob wouldn't be able to read the message that was initially encrypted. Or we could even allow Bob to run in unbounded time, and security still says that Bob cannot learn the message. Okay, so Broadbent and Islam introduced this, and they gave a private key scheme with this property. Then there was a follow-up work by Hiroka et al. That constructed a public key scheme and an attribute-based encryption scheme with the certified deletion property. And there was also this work of Bartosek and Khurana that gave the first sort of generic compiler how to add this property to, a variety of crypto systems. But one thing that wasn't very well understood is this idea of publicly verifiable deletion. Can we make it so that anyone can verify whether a ciphertext was deleted or not? Okay, so it's kind of interesting in principle whether such a property is possible. Okay, so this brings us to kind of the main topic of our paper, which is publicly verifiable deletion. So can we get it, and how hard is it? So there's a little bit of prior work on this. So the first work that constructed a scheme with this property is this paper I mentioned by Hiroka et al. And they constructed a public key encryption scheme with PVD, assuming the existence of one-shot signatures and extractable witness encryption. So pretty strong kind of non-standard assumptions, but it was the very first scheme that was able to construct a scheme with this property. The second paper was actually an earlier paper of mine, which says that actually you can get public key encryption and even FHE with PVD if you're willing to believe a certain conjecture about the itai hash function. Okay, and this was stated as a conjecture. The next paper that addressed this problem of how to construct PVD is this work of Bartosek et al. That constructed it using IO for a variety of crypto systems. Okay, but it seems that all of these papers, seem to fail at actually constructing PVD under standard assumptions. So what's going on? So this is exactly where our work comes in, and we sort of try to construct crypto systems with PVD under standard assumptions. So how do we do it? So what we do is we revisit this second paper that I mentioned, an earlier paper of mine, and we look at the template. And we realize that actually there's a missing piece in our understanding of hash functions that would allow you to prove security if we had a new property of hash functions that wasn't studied before, and we were able to prove certain properties about these kinds of hash functions, then this would exactly allow us to resolve the conjecture and prove that we could get PVD, for example, from LWE or SIS. So what is this missing piece? So in our paper, we introduce this idea of target collapsing hash functions, and we show that we show how to achieve this property called certified everlasting target collapsing. And this new property of hash functions allows us to not only resolve the conjecture that I stated in my earlier paper, which among other things implies that PVD is achievable under LWE or SIS, but it also allows us to prove that this recent encryption scheme by Han, Morime, and Yamakawa actually enables PVD under non-abelian group actions, or more specifically, pseudorandom group actions. Okay, so using this new missing piece, which we call target collapsing hashes, we're able to show that these two schemes actually give us PVD under standard assumptions. And as another result, we also give the first generic compiler for adding this property to a variety of crypto systems from somewhat minimal assumptions, in this case, almost regular one-way functions. Okay, so let me now start by talking about this candidate construction that was in an earlier paper of mine, and how we prove security and sort of find this missing piece that allows us to prove security. Okay, so I'm mainly going to talk about the itai hash function for the rest of the talk, but later, we'll see that actually most of this generalizes to general hash functions as well, and there's no reason to limit this to the itai hash function alone. Okay, so here's the template. So the scheme that I presented in an earlier paper of mine is loosely inspired by the quantum reduction from SIS to LWE. Okay, so this is essentially regef's reduction. And let's consider the following state. It's a superposition of Gaussian weighted vectors x. And we compute a times x in a second register. And here, the superposition is sort of weighted by the Gaussian measure. And it's unnormalized for simplicity. So what can we do with the state? If we measure the second register and observe some image, so let's call it y, we get a really interesting state. We get this sort of coset state, which consists of all Gaussian x that satisfy the constraint a times x equals y. Okay, so geometrically, this is kind of a superposition of vectors that lie in a coset of the so-called perp lattice. So what does it mean? This means that each x in the superposition is short and it satisfies a times x equals y. Okay, in other words, these vectors x are solutions to the inhomogeneous SIS problem. Okay, so why is this useful? So in my earlier paper, I showed how to construct PVD using this idea. Okay, here's how it works. So on a high level, the state that I just showed you has some nice properties that we can exploit for the state on the right. Let's call it the dual state for now. And the state on the left, let's call it the primal state. And it turns out that these two states are Fourier transforms of each other. Okay? So the state on the left is nothing but a superposition of random LWE samples with a phase. So those are kind of Gaussian balls around lattice points. And if we have a superposition of LWE samples, we can use it to encrypt messages, right? So that's why we're going to use the state on the left-hand side in this basis. And we're going to use this basis to encrypt messages because we have LWE samples. And the idea is to delete the state. I'm just going to measure, or sorry, I'm going to apply the Fourier transform and measure. And this is information that is only accessible with an incompatible measurement, because the ciphertext is encoded in a computational basis, but to find a deletion certificate, I actually have to measure in the Fourier basis and find a solution to the inhomogeneous SIS problem. But the intuition is I shouldn't be able to do both at the same time. Okay, so this leads to the following encryption scheme, which I propose. So we essentially do dual regef and superposition. So the public key is a matrix A, which is sampled with a short trapdoor vector. And the ciphertext is, like I said, a superposition of essentially dual regef ciphertext. And we add this bit B as an additive shift. Okay, and decryption correctness is preserved just by classical dual regef essentially. But now I claim that this has this PVD property. So how do we delete a ciphertext? To delete, we just apply the Fourier transform. This will kick the additive shift into the phase. And now if we measure the state, we get a solution to the ISIS problem. And the cool thing is, if we just reveal A and Y, anyone can check whether the certificate is valid. Okay, so this is where we get this public verification property from. Okay, so this is kind of the idea. But what about security? Okay, so now we need to develop some new technical machinery how to deal with security. So how do we do it? First of all, the security experiment we want to consider is essentially the following. We want to say that if we give the adversary a ciphertext that encrypts some bit B, and they return to us a valid certificate, whatever information they have left in their quantum system should reveal nothing about this bit B, right? That's exactly what certified deletion says. And in this experiment, we're going to, just for simplicity, assume that the ciphertext is already kind of represented in the Fourier basis, so the bit B is in the phase. Okay, so how does the experiment work? We sample a random matrix A. We generate a ciphertext that somehow encodes B in the phase. And then we run the adversary. The adversary will tell us a certificate and also have some remaining residual state. And we want to argue that if the certificate is valid, meaning it's short and it's a solution to the equation A times X equals Y, then their residual state should not depend on B. Okay, so this is the claim. And to prove security, this is what we have to show. But in our paper, we kind of take a different approach. Rather than reasoning about this, all we want to do is reason about hash functions in general, okay? And as we will see, it's actually easier to reason about hash functions, and this is kind of what we do in our paper. We develop this formalism that allows us to prove this security guarantee that I just showed you. And here's kind of the simple experiment we need to consider, okay? It turns out that this suffices to prove security, and this is much easier because there's no encryption anymore, and we just talk about hash functions abstractly. Okay, so let's consider the following experiment. It's exactly the same as before. We also have the superposition of Gaussian preimages. But now, rather than encrypting a bit, which is either 0 or 1 in the phase, we change the experiment slightly, and we either hand out the state as it is, or if B equals 1, we actually measure the state before we send it to the adversary, okay? So now the claim is that the adversary, once they present us a certificate pi, they don't actually know whether they started with a measured state or a non-measured state, okay? So this is what we want to show. And we can call this, so what we call this property is essentially certified everlasting Gaussian collapsing. It's kind of a lot, but let's look at the first part of the experiment. So for those of you who are familiar with Unruh's definition of a collapsing hash function, the first half of the experiment is very similar as this notion of collapsing. Okay, so the goal is also to distinguish whether a superposition of preimages was measured or not. But there's an important difference here, namely that this state, this pre-image state, was actually generated by the challenger. Okay, so this target value y in the image of the hash function was generated by the challenger, not the adversary. Okay, so in Unruh's notion of collapsing, the adversary can generate this pre-image state. But in our case, the challenger does it. So y is a fixed value from the perspective of the challenger. Okay, so this is what we kind of call target collapsing. It's similar to how like target collision resistance weakens collision resistance, okay? You do it for a fixed image. So this is kind of where this language of target collapsing hash functions comes in. And then the second half of the experiment just says that once you present a valid certificate, you shouldn't have any information left about whether you started with the superposition or the measured state. Okay, how do we prove this? Our idea is to switch to an entanglement-based version of the game, where we essentially delay our choice of whether we measure the state or we don't. Okay, so here we employ a trick that was introduced by Bartusek and Kurana, which is essentially just let's use entanglement and then wait until the adversary gives us the certificate, and then we do a certain action. Okay, and this representing the proof in this form turns out to be extremely useful. So here's what we do. So we are the challenger. We're going to prepare a plus state in a register C. And depending on the value of this register C, we will either measure or not measure the state. Okay, so that's kind of the idea. And then we wait we keep this kind of entangled state. We wait until the adversary shows us pi, and then we're going to perform a projective measurement on register C. And then all we need to do is reason about this measurement. And in the proof, we show that this measurement succeeds with probability 1, okay, essentially probability 1. And here we're invoking kind of computational assumptions to argue that this measurement succeeds. And then we're also exploiting that this measurement actually projects on a state, on a product state, which is unentangled with the adversary's system, okay? And this allows us to argue that actually the adversary couldn't possibly have any information left about whether the state was measured or not. And this is ultimately how we do the proof. Okay, so let me quickly go back. So if you look at this, there's no reason to think about the itai hash function alone. We could do the same experiment with the general hash function. We could also use a different kind of superposition. We don't have to restrict our choice to a Gaussian superposition. This whole formalism works for general hash functions, okay? And this is exactly what we do in the paper, where we introduce this much broader notion, which we call certified everlasting target collapsing, where we replace the itai hash function with, an arbitrary hash function. Instead of the Gaussian, we choose a certain distribution D, and we also generalize it to various measurements, okay? So in the previous experiment, we measured all the qubits in register X, but you could imagine that you maybe measure like half of the qubits and so on. So we also allow for a general measurement M, which further generalizes this whole thing, okay? And so what is the main result in our paper? Our main theorem says that if you have a hash function that satisfies two properties, it immediately gives us this really strong notion of certified everlasting target collapsing, okay? And as a special consequence, we not only get a proof of the conjecture of my earlier paper, we also get as a side application that this recent encryption scheme by Han, Morime, and Yamakawa allows us to get PVD all from a single theorem. Okay, so here's what the theorem says. If you have a hash function family that satisfies two properties, target collision resistance, which depends on D and M, target collapsing, which also depends on D and M, then it automatically satisfies this really strong property of certified everlasting target collapsing. Okay, so what are these two new properties? So the first one is kind of a quantum generalization of the classical notion of target collision resistance. And the second one is basically this weakening of Unruh's collapsing property where the challenger creates the target during the experiment, not the adversary. Okay, and if you have these two properties, then you have this really strong notion that allows you to get PVD among other things, okay? And so for those of you who are familiar with the collapsing notion, this may seem surprising because we know that collapsing is actually a strengthening of is a strengthening of collision resistance. So why do we introduce these properties separately? Well, it turns out once you consider the target version of these two properties, this doesn't seem to be true anymore, that collapsing implies collision resistance. So we leave it as an open problem to actually resolve how they're related, but we believe that they're actually separate. Okay, so that's why in the theorem statement, we treat them separately. Okay, so this is our main theorem. And now let me summarize the main contributions of our paper again. So in our paper, we give a natural weakening of collapsing, which we call target collapsing. Here, the difference is that the challenger creates the target image. We show that hash functions that have certain basic security properties automatically satisfy certified everlasting target collapsing. And if you have this property, you can say things about publicly verifiable deletion. This is what we do in our paper. We showed that this candidate scheme in my earlier paper has PVD. And we also showed that the scheme by Han, Morime, and Yamakawa enables PVD. Okay? And then as a final result, we give this generic compiler that adds PVD to a variety of crypto systems. Okay, so I want to finish with two open problems. So the first one is what I mentioned just now, which is target collapsing actually different from target collision resistance? Is it true that target collapsing doesn't necessarily imply that target collision resistance also holds. And another open problem that that I care about personally is, are target collapsing hashes as a concept useful for other things, not just certified deletion? Okay, so it'd be really cool if anyone found new applications of this definition. Okay, that's the end of my talk. Thanks so much for the attention.
Great, thank you. We've got a couple minutes for questions.
Hi, thanks for the talk. So this target collapsing property depending on this measurement and distribution D.
That's right.
I'm just wondering if you replace the hash function to random oracle, for which M and D does it satisfy the target collapsing property?
I think this should be handled by the theorems in our paper. So if you look at the theorem statement, I think your question should be answered by the theorem statement. So if the random oracle satisfies these two properties, which I think the random oracle does, then you immediately get the statement that you were asking about.
So you mean for every choice?
So the random oracle is collapsing, and collapsing holds for any distribution D, right? So then I think what you're asking is, does it hold for any D? I believe the answer is yes. And for the measurement M, that I'm not sure about. I would have to think about how it depends on the measurement. Yeah, I don't know. I would have to think about it.
I see. Thanks.
Okay, seeing no other questions, let's thank our speaker again.